Yeah, you can start.
There are very few participants. 26 only, including myself, yourself, Amber, and all that. So do I start?
Yes, sir.
Have you people had a chance to go through the notes? Hello? Because I think yesterday it was already posted, though yesterday you could not get a chance, it was not posted. Still, it is possible that you did not get time or anything. So I want to know whether you had any.
I have gone through the but not rigorously, just skimmed through the pages.
Gone through is just what I don't want you to be master of this.
Yeah.
Okay. Whether you have gone through,
Yeah.
whether you had a chance to look it into it.
Yes, sir. Yes, sir. I have looked into it.
There is only one person who says yes out of 20. Huh?
I have also, sir.
Okay. So who else? Nobody? By the way, his tutors are there.
I'm here, sir, and probably Samir is joining.
Devendra is there. Did you have a chance to look into the notes?
Yeah, I looked into notes and prepared some problems, so we will discuss after you.
You are ready for the tutorial class also, huh?
Yeah, I mean,
Good. Okay. Who is the other tutor? I don't remember his name also.
Samir, he is joining actually in 2 minutes.
Huh?
Samir Hajra will be joining in 2 minutes.
Okay. So, what about any others? Had they seen the notes?
Yes, I have seen also.
Do you have any comments? Hello.
If you people understood everything,
Everything understanding, even I don't. Okay.
no, students.
Everything understanding is, only Ramakrishna Paramahamsa, that kind of people. We are not of that caliber. Okay. We don't understand everything. That is not, but we try. We keep trying. Okay. So right now, what have you seen this? Have you gone through? Did you get a time? So this is just an organizational question, not a question to test your abilities or test your understanding. So just 3 or 4 responses. That's all. Huh? So you see, that means that the effort I am putting is not being properly used. So it's going tangentially somewhere else. All right. So anyway, yesterday's part, have you any question? Have you any remark? Whatever we did yesterday, 1 hour. For that, you may not have to go through this one, but at least you have to have some thinking on that after the class. Otherwise, it is just after class to class, that's all. Nothing has gone into your mind. So have you any questions, doubts?
I do not have any question, but I was pondering about the thing that in the last class we have completely found the rational points on quadratic curves. So, so is there any other method or some kind of tool to find the rational points on any cubic curves?
That is a big problem. There are so many methods. You see, I have told you for a quadratic equation, okay, on a plane, wherein the equation is given by rational coefficients, polynomial with rational coefficients. There is a solution. As soon as you take cubics and so on, there is no way, there is no general method. X power n plus y power n equal to 1, which is simplest one, n greater than or equal to 3, it cannot be given by rational coordinates. Right? So this method, though it looked so wonderful method, solve the problem for quadratic, it's not going to give you, take you far away. But you should learn this method also, because its failure also tells you something to attack things elsewhere. Okay, cubic equations, which go under the general name of elliptic curves, finally solved the, actually, they didn't solve it, it helped to solve Fermat's last theorem, right? So there are methods, but that is not the aim of this one. The aim of the first lecture is to emphasize the importance of parameterization. I gave you some example of that one, okay? Other than what is there already in your prescribed book, Presley. So my aim is not to just repeat what is there in Presley's book. I want to help you to read that book, so that I am trying to take his own concepts as far as possible, as far as I agree with him, and tell you a little more about, what he hasn't told. That's all. Okay. So let's go ahead with now the study of curves. Okay. So today we will study arc length. Once again, I presume that in calculus course you have already studied the arc length. So quite often definitions such are given here only to recall as well as to fix our own notation, because you might have done it in a different notation and so on. Okay. So this is not the start. If I start this course, for example, for a calculus students, I will do it in a quite different way. So here I am doing it quite fast. Okay. More details of this one, even in the book, it is faster. You can have it in the from the book. Okay. Having said that, let us start. Arc length of a parameterized curve. See, I will all the time stick to parameterized curve from once for all now. Okay. Arc length of a parameterized curve. Now I have restricted to closed interval only for convenience. Soon you will see that this restriction is not necessary. It could be any interval j to Rn that is measured from a given point. A reference point is there. The length has to be measured from any given point, from where it starts and so on. Okay. Given point gamma t naught. So gamma t naught is a point on the curve of a C1 function. Any gamma could be just a C1 function. Actually, finally, we will go to apply to smooth functions, right? Smooth curves. Given by SU. Okay. SU is a definition now. This is U is in a point of this one. L gamma U is another notation here. Okay. It is integral of T naught to U, integral of the norm of gamma dot. Gamma dot is a velocity vector or the tangent vector. Look at the norm of that, integrate it. So this coincides with our standard notion of that distance traversed is what? A constant velocity, velocity time into velocity into time. So here it is integral, because gamma dot is not a constant thing here. Not. So it's integral of T naught to U, norm gamma dot. Norm gamma dot is the speed, right? So this is definition. This function, there is a norm coming here. So pay attention to this one. Gamma dot is an element of Rn. So norm of that is a real valued function, non-negative, right? The norm function itself is a very nice function, continuous on the whole of Rn and differentiable outside 0, 0, 0. Any number of times. It's a smooth function from Rn minus 0, 0, 0 to R plus. Okay, so that's why this thing makes sense. So this is just a real valued function. I'm integrating it from t naught to u. All right. A parameterization of a curve is called a unit speed parameterization or arc length parameterization. These are the two terminologies which are used all the time. If what happens, if the speed is always 1 for all the points t beyond t. Okay, this 1 is a normalizing factor. You could have taken a constant speed. Then again, you'll have to keep on dividing by that constant and so on. That's like changing scale, right? So let us say norm of gamma t is equal to 1 for all t. Then this is called a unit speed parameterization. Okay. Once this is the case, what happens to the integral? Integral of a constant 1 from t naught to u is u minus t naught. Right? So it will become just t minus t naught. If you s of t h b, there's a typo here. Otherwise, it's s of u is u minus t naught. Okay. Notice that being parameterized by a unit speed parameterization is very fragile. If you change parameterization, it will change. So there is no guarantee, right? So it is very fragile. It's almost there is a uniqueness here. It's quite rigid in that sense. So that point you have to be careful here. We can easily destroy it by a change of parameterization. Also, in general, we cannot guarantee that a given curve, it can have reparameterization such that it becomes a unit speed curve. We have not proved it. So why I am telling all this? Because I am using a special thing here. What about other curves, you will ask, right? So that is the remark here. So how far can you go? Suppose you have started with some arbitrary curve. Okay. It is not always possible to describe the whole thing by arc length parameterization. The moment arc length parameterization is there, the dot, gamma dot is non-zero. It's non-zero vector because norm is equal to 1. So that is an automatic necessary condition that if you can find a parameterization which is a unit like this, unit speed parameterization, then the curve must be a regular curve. Okay. Or what may happen is you throw away the points wherein it is not regular, wherever the tangent vector is 0. The rest of the curve, maybe you can do, right? Without that, you cannot. So you throw away those points. The theorem here is that it is possible. Arc length parameterization is always possible for a regular curve, for a regular part of any curve. Okay, so that is the theorem here. Every regular curve has an arc length parameterization. Okay, moreover, any two arc length parameterization of the same curve are related by a translation in the domain. What is the meaning of this one? Suppose you have an arc length parameterization like this. Okay, then you can just take a new parameterization S prime of whatever is some t minus t naught. In the domain itself, you subtract. From AB to Rn, you have from A plus some lambda to B plus lambda, you can have by subtracting, take any t minus lambda, and then apply S. So that is the one, obviously, because if you change the coordinate from t to t plus something, then the norm of this one doesn't change. Whether you differentiate it to t or t prime, it is the same thing, because the transformation t minus t naught the derivative of that one is just 1. Right? Therefore, that is always allowed. Changing the parameterization by an additive constant in the domain. This theorem says that is the only thing you can. That is obvious because you will see. First, let us try to see why this is possible, and then you will see the automatically theorem will tell you that the uniqueness part will automatically come. Okay. All right. Start with a regular curve AB to Rn. Okay, that means what? The tangent vector is not 0. Okay. For each u in AB, consider the restricted curve A to U up to A to U take. That's all. So that is gamma u. Okay. Notice that since gamma is regular, it follows that now SU, which I have defined as the length of gamma u restricted curve. What is this one? It is integral of from A to U of gamma dot d dt. Only up to U you take. That is the meaning of this one. L of gamma u. This is just a different notation for SU. Okay. As you keep increasing the interval, length of interval over which you are taking the integral, because you are integrating a non-negative function, it will be strictly monotonically increasing. Actually, a positive function. Gamma dot is not 0. So, strictly monotonically increasing function. Okay. Its derivative by fundamental theorem of integral calculus, it's just norm gamma dot. That's what we are integrating this one. So, derivative will be this one. So, it is positive. Therefore, it is what? It is a diffeomorphism. Its inverse is also differentiable any number of times. Okay. Hence, the diffeomorphism of the domain of AB onto it's a continuous function. Okay, on a closed interval. So, what should be the image? Image will be another closed interval. This is elementary topology of real numbers and real line. Okay, continuous functions attain their both supremum infimum, and image of a interval is again an interval intermediate value theorem. Okay, so it's again an interval CD. Therefore, its inverse for S inverse from CD to AB is also a diffeomorphism. Okay, both phi and phi inverse are differentiable. That is the whole meaning here. With its derivative, what is the derivative of the inverse? It is the multiplicative inverse of the original function, 1 divided by norm gamma. It is elementary calculus of one variable. Okay. So, you know what happens to this arc length function. Arc length function from AB to CD is a diffeomorphism. So, what is the trick? Trick is to use this diffeomorphism to get the different parameterization. All right. So, we choose reference point of S. Let us take it gamma A, because after all, we have taken the interval from A to B. Okay, that is why this A is there. Okay, otherwise, the interval could be any J. Then, of course, C will be 0. Why? Because what is C? C is the minimum of all these interval and all these values. Integral from A to something. A to A, that's C. Because gamma S of A is just A to A integral. So that's 0. Okay, C is 0 and D could be some D. That's all. Okay. So D is what? It's the full length integral from A to B, the entire. So that is the full length L of gamma, the total length of the curve. Consider gamma twiddle now from this 0 to L gamma. This is C to D. I have written as 0 to L gamma to Rn. by writing test, first S inverse, come back from this interval to AB, then follow gamma. This is gamma twiddle. Now use ordinary chain rule for differentiation. Gamma twiddle will have norm equal, derivative of gamma twiddle will have norm equal to 1. Okay, it is gamma dot twiddle, gamma dot into S dot, which is, because we have taken S, 1 divided by gamma, so 1 divided by norm of gamma, so they will cancel out. Okay, so we have found the Arcland parameterization here. Why we have found it? Because of the uniqueness that this, it cannot be anything else, right? If the total, after composing the function, the norm of the function is 1, original function should be the one of one, should be the inverse of the other. So that is why this is forced on us. So once this is forced on us, the only choice now left us is changing by adding a constant. So that is why the translation ambiguity actually comes, because you still have the choice of where to start, reference point, where you are measuring from. Okay, so that is still there. That is why the additive constant is there. Like in any integration theory, definite integral, the starting point, okay, will tell you the additive constant. What is the additive constant? If your starting points of two integrals are the same, then the additive constant will be 0. Okay. All right. You see, in a introductory lecture, I would have given examples, circles, parabola. All these things are part of calculus course wherein you must have done it already. All right. So I will not waste my time on that one. There are exercises. If you want, you can discuss it with your tutor or elsewhere. If you have any questions of that after try, you are still welcome to ask. But I assume that you know such things. Okay. So let us go ahead. Let us do another important concept here now, curvature. Okay. So this may be somewhat new to those people who haven't done any differential geometry altogether. Okay. Though the word curve is familiar to them now, curvature. Curvature is something which we should measure the how much the curve is curved, right? Common sense mathematics leads us to look for the rate of change of direction of the tangent curve, tangent vector to the curve. Okay. If in a straight line, the direction is always the same. The tangent to a straight line is the same line, right? Therefore, or parallel to the same line, you can say. As a vector, it's just a parallel vector. Whereas, if the road is curving, okay, no matter how fast you are going, okay, the curve is a curve. You are changing the direction. Only thing is, in reality, if there is a curve, you will have to slow down your speed. Otherwise, you may be in trouble. So that's a different aspect. Okay, that can be discussed elsewhere in dynamics. So right now, what we are interested in is how much the road is curved. Therefore, let us assume that all the drivers are driving the same speed, unit speed. Okay. unit you can define, whether it's 1 kilometer per hour or 1 kilometer per second, etc. This is one. So there is no quantities assigned to this one. This one is a pure number. Okay. So we are interested in only the speed component, right? Therefore, we should choose right in the beginning unit speed parameterization. That's what I told you, but all the drivers are driving at the same speed. Okay. With this preliminaries, let us make the definition. Take a unit speed car, okay, then its curvature function is defined by kappa t, this is the notation, is equal to norm of the second derivative of gamma, the derivative of the derivative. That is acceleration vector, you can say. If gamma t, you call it as tangent vector. So we declare gamma double dot t, we don't have any name, but physicists would call it now acceleration vector. Okay. So kappa t is the norm of that, norm of this vector. So this is a real number. Okay, non-negative real number. Okay, this should measure how the direction, rate of change of direction, not the total curvature, rate of change of direction of the moving particle. All right. So this is called kappa, the curvature of the curve now. Notice that in the definition, we have left out the case of curves which are not regular, because gamma is defined to have mod gamma dot equal to 1. So it must be non-zero vector, right? It's non-zero vector. So this is left out. In fact, we can include any curve, but consider only regular points of the curve. At that point is defined. A more important question here is that why only use arc length parameterization? Okay, you are measuring only that one, but why insist on having the curve itself is arc length parameterization? Indeed, this one is a burden on us to some extent. Okay, on the other hand, to understand what is going on to begin with, this assumption is good. So the simple reason for the positive side of why we assume is that computationally this becomes very simple. Okay, it is not a logical necessity. All right, so that is why we assume that it is USP. On the other hand, there is a negative aspect also here. Starting with a curve which is regular, okay, you can get a regular parameterization, but getting an arc length parameterization is a burden. Is it always possible? This we have not answered yet. Okay, what I mean by saying that theoretically it is possible for a regular curve. We have got S inverse, unique one, and so on. But finding that expression when you are dealing with some explicit curve, that is a problem. Here I am talking about, suppose the curve is described. Somebody makes a survey and he has described the curve. It is not arc length parameterization. It is some simple curve, maybe, or maybe it's very complicated curve. Okay, some data is there. You to find an arc length parameterization in general is impossible also. What I mean by saying that is, you have to do some integral formula there, right? That can collapse. It may not give you a closed formula. Very simple example is there. Look at the ellipse. Any ellipse which is not a circle. The arc length cannot be found in a closed formula. These things are very, very important. They are called elliptic integrals. Okay. So what I am now trying to do is take any regular parameterization. Okay. Theoretically, there is a arc length parameterization, and we have defined kappa. How it is related to the original parameterization? Directly, let us have a formula. Bypassing the arc length parameterization. Let us have a formula. So that is the aim of this one. Okay. The formula for curvature in terms of the original regular parameterization. So suppose now I am having some notation here. This is our temporary notation, keeps changing. Gamma twiddle from CD to Rn be the arc length parameterization of a regular curve gamma from AB to Rn. This is the same notation I have just introduced. Starting with a gamma from AB to Rn, gamma twiddle is from CD to Rn. So this is the picture here. So AB to CD, this is the arc length curve, arc length function, right? And this is the gamma twiddle. How gamma twiddle was defined? You take S inverse and go to gamma and composite gamma. S inverse composite gamma, right? It is the same thing as saying that this diagram is commutative. Gamma twiddle composite S, the other way around, is actually gamma. Okay, gamma is actually gamma twiddle composite S inverse is same thing as saying. All right. Pardon? Huh? Somebody is shouting, but I can't hear. Hello, is it some participant or somebody else?
Sorry, sir, somehow the mic was on.
Oh,
Yeah, by
okay,
mistake.
okay.
Yeah.
Okay. Okay, so any questions here, by the way? See, I'm not doing anything new here. I'm using the definition of arc length parameterization, the new curve, out of the old curve gamma. Okay. So temporarily, let us denote the differentiation with respect to T and S by dot and dash. Okay. With T, we'll use dot following Newton. This dash, S is dash general. Okay. By the way, Newton and Leibniz, both of them independently established or invented differential calculus, derivative, concept of derivative. Okay, Newton followed T notation and a dot for derivative. T for him representing always the time parameter. Why? Newton was all the time interested in planetary motions. The planets were particles and they moved, and the movement was a parameter of T, parameter of time. So he was not interested in any other thing. So he found out this thing, but then this has applications everywhere throughout our life, in all walks of our life. Okay. So the parameter need not be just time, it could be any other, some real number. So that is why general people use S. I think Leibniz used different notations altogether. Okay. Of course, nowadays we are using very simpler notations as compared to the olden days. So begin with this equation, gamma equal to gamma twiddle composite S. Okay. S dot square, there is an equality here, equal to gamma dot gamma dot. That is the definition, right? S dot is the derivative of the arc length function, which is norm of gamma dot. The square is gamma dot gamma dot. Gamma dot is the dot product of the vectors. Okay. the central dot is the dot product. The top dot is the derivative. So gamma dot, there must be equality, S square equal to this one. That equality is missing here, sorry. Apply the chain rule and Leibniz rule for product of function and a function, ordinary real numbers to real valued function for differentiation successively in whatever I am doing here. You will get some equations. First one is gamma dot, derivative of this one by chain rule is S dot times gamma to the prime. This prime is what? Derivative with respect to S. So that's a chain rule. Here, S dot square, when you differentiate, twice S dot into S double dot is equal to the derivative of gamma dot is twice gamma dot into gamma dot gamma double dot. The two cancels out, that's all. Okay. All right. Differentiate once more. Gamma double dot, okay, is now I have to use Leibniz rule here. Okay. S dot into derivative of this one, okay, with respect to S. So gamma to double dot, and then S has to be differentiated, S dot. So one more S dot will come. Okay, that is one factor. Plus, this time you differentiate S dot, so S double dot, keep the other factor as it is, that is gamma to the prime. Okay, so this is the second derivative. Now, multiply the whole thing by S dot square. Okay, what do you get? Because we are getting S dot here, that's why you want to simplify, you want to use this equation, you have to multiply by S dot, but there is a square here, so multiply by S dot square. S dot square gamma double dot is S dot to the fourth into gamma twiddle double prime plus S dot square into this factor. S dot into S dot square is this one. Okay. S dot into gamma twiddle prime is gamma dot. So I'm using the S dot square once with one S dot, one factor here, combining which I get gamma dot gamma double dot plus this gamma dot into this gamma dot. Okay. So this factor multiplied by S square, S dot square is this one for product of these two things. So we have got expression for gamma double dot on this side. And this is what we want in terms of gamma double dot prime, right? So therefore, this gamma double dot, gamma twiddle double prime is nothing but this minus this divided by S dot to the fourth here. See, there is another typo. Okay. You can rewrite it as S dot to the fourth is the same thing as norm gamma dot to the fourth. Because S dot is nothing but norm gamma dot. So this is the formula for gamma to the double prime. You see, now gamma double prime is earthing parameterization. Okay, norm of this is kappa. These are all in the original parameterization. Gamma dot is the original parameterization, regular parameterization. So this is the complicated formula. If you give like this, it is nowhere, it is not at all clear why it is represent the physical interpretation of kappa as we have started. Whereas if you start with Artin parameterization, it's very clear. Okay, but now we have got the formula also to satisfy all those people who are interested in computation. Okay. Got it? Very straightforward. I have done this one so that you should feel that there is nothing very tricky things are involved here. And you should know how to get out of these things. or ordinary differential calculus, Leibniz rule, chain rule, etc. are used here. Okay. Any comment? No comment? Let's go ahead. Now I use something special with R3. So assume n equal to 3. This formula is valid in all the dimensions. Okay. Now come to n equal to 3. You have this extra structure of vector triple product, cross product is available, right? And you have this formula which I have to use. Now I have to assume that you know this kind of calculus. A cross B cross C is A dot CB minus A dot BC. Okay. So use this to simplify this funny thing here on the right hand side here. Okay. What we get is, see, this is something, this dot, this into gamma double prime, this dot, gamma double prime, this one. So it's a difference of these two. This is precisely equal to gamma dot cross gamma double dot cross again gamma dot. Okay, you have to take it correct order. Gamma dot cross gamma double dot cross gamma dot. Put the brackets on the second part here. You know that this cross product is non-associative. Okay, so you have to put it correctly in the correct factor. Okay, divide by gamma dot to the 4 as it is. So this is the formula now for gamma dot prime. You take the norm, then you get kappa. Okay, so let me write down that formula also. When you take kappa, it's a norm of this one. You just get gamma, anything A cross B, the norm is norm of A into norm of B, right? So norm of this is one gamma dot comes out, that cancels out with one of the factors here, gamma dot cube, and in the numerator it is just norm of gamma dot cross gamma double dot, which is the same thing as, you can interchange the order here, it will be just minus of that. So when you take the norm, that minus disappears. So this is one. What is this one? This is the unsimplified form of this one. This is general norm of this one, which is valid in any dimension. This first formula is valid in all the dimensions. This is valid only in R3 because I have used a cross product here. Okay, at least in R3, you have not very complicated formula for kappa. Okay, still it is complicated than just taking gamma double dot and it's not. All right. So now umpteen questions can be asked, compute this, compute that, exercises and so on. They are there in the book for your practice. I have practiced. If I do it, I will get more practice. But do you get it? You want to get it? You have to do that. Okay. Without dirtying your hand, there is no way to learn. The first formula is valid in all dimensions, whereas the second one is valid only now. Now, I will discuss only things inside dimension 2 and 3. Okay? How much more time I have? It is 7:30 or what? 5:30 or what?
Yeah, it is 15 minutes till there, sir.
Okay, good. So we shall concentrate on plane curves. Okay, next time we'll do the dimension 3 curves. We begin purely a topological result. We will only state it today. The proof of this will be given you to the last week, in the last week. Okay. So this is called path lifting theorem. people who have done some algebraic topology will see that this is a very easy consequence of that theorem. That theorem I am going to do in the last week. That will be used several times from several things in various applications of whatever we are doing, whatever the book is doing. Okay. So here I am going to state it. Start with any interval and a function into the unit circle. This S1 is a unit circle. Okay. Take any continuous function. All right. Take a point T0 inside J. Take a point phi naught inside R such that this psi of T0 is cos phi naught, comma sin phi naught. Remember, every element of S1, the unit circle, can be written like this. Right? So what is this phi naught? Phi naught is some real number. So this is the unit. Start with a function and start with a point. They are related like this. This is not arbitrary. With a point here, this phi naught must satisfy this equation. Because psi of C naught is something that phi naught has been chosen this way. That is all. All right. Now, there exists a unique continuous function phi from the interval into R such that this original function psi t is cos phi t plus sin phi t for all t inside J. One single angle you have chosen to represent a point on the circle. The continuous function taking real values, entire thing is determined. So angle determining. So this is purely point set topology. Okay, of this function angle, which is expressed very nicely by the in your analysis course. You know, the professor started with exponential function. That function will be used here. In fact, exponential function is the starting point of in the book of Rudy, which is a prescribed book for you. Okay, but that is not part of syllabus. He does that one. Why? Because that is the most important function for him in the real analysis and complex analysis that he is discussing. It is there everywhere. It is used in topology also. So this is the crux of the matter here for us. But I will postpone the proof of this statement. Okay. Exponential function restricted to the y-axis will be used here. All right. Okay. Any questions? Let us go ahead. I'm not going to prove this one. I'm going to use this now. Okay. Now start with any unit speed curve inside R2. I am specializing into plane curves now. Plane curve means what? We are working in R2. Let gamma dot from AB to S1 now. Why? Norm of gamma dot is 1. That's a unit circle, unit vector. So it's inside S1. Okay. So this is a smooth function because I have started with my assumption is always smooth function. Gamma is smooth function. That would be a problem. Choose a phi naught belonging to R. So set gamma dot A. Now I am applying this phi to my gamma dot. Gamma dot A is cos phi naught to sin phi naught. So I am applying this proposition here. Okay, by the previous proposition, the entire gamma dot S can be written as cos phi S plus sin phi S. Okay, where phi is a smooth function, we call phi the turning angle function of gamma. So angle of not gamma, but actual gamma dot. So that's why how the change in gamma dot keeps on. Gamma dot is function, so the angle function here. So that will depend upon how gamma is turned, the particle is turned. Okay, it's called turning angle function. Okay, note that it is unique up to an additive constant. The choice of this phi naught, okay, that will determine the function. But I can choose phi naught in many ways. How many ways? See, phi t naught, the unit point is given, t naught is given from it. How many choices are there for v naught? So cos phi naught plus sin phi naught must be the same vector. How many choices? They are all additive multiples of phi naught by 2 pi m, right? Where m is an integer. So additive constant is there. All other phi which will give the same cos phi plus sin phi must differ by a additive constant, namely by a multiple of 2 pi. Okay, integer multiple of 2 pi. Okay, 2 pi n belong to z. Okay, so once phi naught is chosen, phi naught plus 2n pi will also satisfy that property. Okay, so that is the meaning of determining what is this angle. Angle is never properly defined in that sense. There is an ambiguity always, right? So this is the idea of using this. Once you choose that, the ambiguity disappears, so the whole function can be chosen continuously. Not only that, after that there is no choice. It is unique. And if the original function is smooth, the choice function phi will be also smooth. If gamma is smooth, gamma dot is smooth, automatically this phi will be smooth. Okay. Now, having done that, look at the derivative of this gamma dot itself. Okay, so I am taking this gamma dot here and differentiating minus sin phi cos phi into the derivative of phi itself, d phi by ds. So this is what it is. What is this vector? It is got by turning this vector at 90 degrees in the anti-clockwise direction. Okay, minus sin phi comma cos phi. This is x, this is y. The vector which is perpendicular to this one is minus y comma x. X comma minus y comma minus x is also perpendicular, but that will be in the opposite direction. Okay, this is got by turning it, okay, obtained by rotating the tangent vector, namely cos phi sin phi, by pi by 2 in the anti-clockwise direction. Okay, so that is the meaning of this. Now, this is called the signed normal of gamma. Okay, the tangent is the moment curve is given, the tangent vector is given. So normal is also given uniquely. So it's called signed normal because there are two normals, right? In R2, if you are one vector, how many perpendiculars are there? Unit perpendicular. There are two of them, right? The one which you have chosen is on the anti-clockwise direction. So that's called signed normal of gamma. And it's denoted by NS. So this is the notation followed in the book. If you use complex numbers, what is the meaning of turning at an angle pi by 2 in the anti-clockwise direction? It is just multiplying by I. So NS is nothing but I times gamma dot. This notation is possible only if you think of gamma dot as a complex number. So that is possible because we are working inside R2. Okay. So I have defined what is the meaning of signed normal. Normal means what? Perpendicular to the tangent vector. There are two different perpendiculars here. No, I mean unit perpendiculars, unit normals. So you have to choose one of them. How you choose? By this formula. Okay. What is the meaning of this? I am telling you. So if you don't, if you cannot decide that anti-clockwise, clockwise, and so on, don't worry. You have to follow this notation. There is no ambiguity here. Okay. There is no ambiguity in the proposition. There is no ambiguity in the choice here. Okay. So we can now define a refined version of kappa. You see, kappa was defined as a norm of this one, right? As some real number, which is the length of that. There is no sign assigned to this. Curvature was defined as a non-negative function, but curvature can have negative meaning also. Can be negative also, depending upon how you measure it. That is why we have to give a different function here altogether. That is possible if you choose the norm correctly, the normal correctly. Okay. The signed curvature of gamma is defined as Ks of gamma, is notation, is defined by this formula. Gamma double dot, if you don't take the norm, take the normal vector, okay, ns times Ks of gamma. Why I can do that? Because this is perpendicular to gamma dot. There's only two choices for this. So this function is well defined, therefore. Ns, once you choose correctly, there is no choice for this one now. It has to be plus or minus. It need not be plus always. Ks of gamma. If you take the norm, if you take the modulus norm of this one, you will get modulus of Ks of gamma into norm of that, that is 1. Okay. So then the sign disappears. It will become only a non-negative function. Now Ks of gamma can be negative also. Okay. Your curvature may be going the other way around. The curve may be turning this way. The curve is turning that way. It also makes sense here now. Which way is also makes sense. That is why this is a better formula for curvature function. This is called signed curvature. Okay, it follows that if you take Ks, which is just nothing but d phi by ds, okay, mod Ks is kappa. Okay, so Ks, if you just forget about this part, just differentiate with respect to what you get is this Ks d phi by ds. Okay. Consider the curve. Now I'm giving you an example. I am not sure whether this example is there in your book, but this example I am going to use in the general theory later also. That's why I'm doing it. Okay, we will do this one and be done with today's lecture. Start with a curve which is the graph of some function. F is smooth, t comma ft. It's a very special curve. Okay, let us determine Ks of this one. Okay, without reparameterizing. Unnecessary. Why should you parameterize the graph of a curve? Is a nice parameterization. Okay, from this formula, gamma twiddle double prime is this formula. Okay, compute all of them, whatever. Gamma dot is what? 1, comma, f dot. Gamma double dot is 0, comma, f double dot. Gamma dot square, what is the norm of this one? It's 1 plus f dot square. Sorry, norm square, f dot square. Gamma dot gamma double dot product of these two things, 1 into 0, which is 0, plus f dot into f double dot. So I have computed quite a few of them. Okay, whatever we wanted here. Therefore, gamma double dot double prime, gamma twiddle double prime is nothing but, see, this vector will come here, f minus f dot f double dot 1 plus f dot square, the whole square. Okay, so this is norm gamma dot square of that. That is why it's norm fourth. So one of this is norm. So this is my gamma double dot. Since the signed normal is got by turning the unit angle to 90 degrees, okay. So this is the unit tangent here is 1 comma f dot, right, divided by the norm. This gamma dot is not unit norm, so divided by the norm, and then you turn it, namely you change the x and y coordinate, change the sign of the y coordinate, and what you get is minus f dot comma 1 divided by the norms. Your norm is 1 plus f dot square. So if you use this, then what you get is Ks is just f double dot divided by 1 plus f dot square raised to 3 by 2. Okay, so in simplification, what you get is, this is the formula. Ks is just this one. The signed normal is f double dot divided by 1 plus f dot square 3 by 2. So this is the simplest thing other than signed, other than the unit speeds curves. Okay, for the graphs, f is given, immediately you can write down the signed normal, signed curvature. Okay, right? So finally, there's a theorem here which is of purely what? Purely theoretical importance. I will print down this one. I think I am not going to use it anywhere. What it says is, start with any smooth function, no matter what it is. It is the signed curvature of a function. Okay, so this is of theoretical importance. It is called solving by just integration theory. Okay, so I am not very keen on this one. I have put it here because it's also there in the book. We can read it very nicely. It's very, very easy proof. Finally, start with any function f, integrate it, get the theta, cos theta, sin theta, integrate that will give you the curve omega. There is a second order differentiation. Once you integrate, another time integrate, you have to integrate twice, you get a solution. It tells you there are two parameters, twice you have integrated, so there are 2 points of at which you can have some choices in order. Up to that, it's unique also. Okay, so that is the theorem here. So it is very easy to understand. Read it yourself. Perhaps I am not going to use it anyway. So what is the gist of this one? Is that precisely that any function can be thought of as a signed. Okay, having told you that, I must tell you that start with very simple functions. The curve which you get can be very, very complicated. Okay, start with a zero function. What do you get? You will get a straight line. Start with a constant function. What do you get? You will get a circle. So these are easy to understand, but slightly more complicated functions. So start with the identity function, t going to t. What do you get? You will get a surprise function. Okay, so that is why. So it is interesting to see some of these things, but I don't know whether I have any use for them. For example, you take k is equal to s. I mean, identity function. the curve that you get is called Cornus Spiral. It is applicable, it has very important in physics, namely theory of lights, diffraction theory. Its picture you can see in the book, so I don't want to draw it here. See the picture, page number 50, you will see that picture also. Okay? So thank you.